Okay, so we are going to look at a variety of solids, and the way that we're going to categorize them is what kind of atoms do they have, or molecules or particles, and what kind of forces exist between the particles. So that's why this note is connected to what we did yesterday, because we needed to make sure that we knew what covalent was, what ionic was, etc. Okay? So in general, the solids, you determine what kind of solid you have based on inter and intramolecular, so it can be both. And and so then the type of it, which is usually correlated with how strong they are, will affect the kind of solid there is. So for example, we'll look at the difference, say, between diamond and graphite. So diamond is considered to be the hardest substance on Earth. Graphite is what's in your pencil. You can sharpen it, okay? And all it is a different arrangement of the atoms. Makes very different properties based on the strength of the forces. So there's two very broad categories. Crystalline have ordered, organized arrangements. So what that means is they're predictable. So these are the ones that we're going to focus on, these 5 categories. So if you have the note printed off there in front of you, it says in this order: atomic, molecular, network, ionic, and metallic. Okay? So most of these, you can look at the name and figure out, that gives you a clue to what you're talking about. So atomic solids have atoms bonded to each other. Molecular are the different kinds of molecules, polar, nonpolar, and ones that can make hydrogen bonds. Network is unique, so maybe you've never heard that word before. Ionic will be metal and non-metal, just like an ionic bond. And metallic will be transition metals, just like metallic solid has metallic bonds with transition metals in it. Okay? So we're not going to push out of our brain things we already know. Amorphous solids have indistinct shapes. They can be very unordered. Glass you can make frosted glass, you can make clear glass, you can make colored glass, stained glass, whatever. Very, very, very different. So, and rubber, same thing. Snow tires even, and regular tires have different kinds of rubber, different cross links. So very unpredictable. This is the last slide you're ever going to see about amorphous, okay? So we want to be able to predict the properties of the solids, and if they're unpredictable, then that's difficult to do, okay? All right, so one of the big things about a solid is that it usually forms a cube. And when you have, or if you continue in chemistry, then you can actually spend time calculating what kind of cubic structure exists between particles. That is definitely beyond what we need to do, okay? But this picture is trying to show that these atoms are arranged in this cubic structure. So atomic solids have atoms between them, okay? So the clue is in the name. And the force they have is dispersion only, okay? So as we talked about yesterday, dispersion forces are the weakest, which means that they have low melting and boiling point. Okay, so these, because they have very weak dispersion forces, then they are very weak solids. So in fact, this sentence or this phrase here, it almost, you're like, Miss, how this doesn't even make sense. Noble gases in the solid state. Gases are solids, right? So you can think of this like CO2 or dry ice, which is solid carbon dioxide. If you've ever got to play with that, it sublimes. It doesn't even change into a liquid. It goes right from a solid to a gas. So it's not a super strong solid. So something that is gaseous wants to be a gas. Yes, you can put it under an enormous amount of pressure and make it be a solid, but it's not going to be long-lived. So it's very easy to change this back into a gas, which makes sense, okay? So weak forces, low melting and boiling point. This is a very, very weak solid. Okay, so molecular solids made up of molecules. Okay, so again, clue is in the name, but there are different kinds of molecules. Okay, so we have nonpolar molecules, which again would be weak forces. You can also have a polar molecule, which then there's two possibilities. So for nonpolar, where it's weak dispersion forces, they have low melting and boiling point and are not very hard, so they're soft. Again, because the forces are weak, okay? So then polar, you have two choices. It can either be hydrogen bonding or dipole-dipole. So then, just like we've talked about before, hydrogen bonds are the strongest intermolecular force, which means they are the toughest solids. So solid H2O, which is ice. Ice can exist at room temperature for a little bit, right? It's a pretty good solid. Whereas carbon dioxide, which is dry ice, it is a polar molecule. However, if I had it in the classroom, it would be subliming. It would be changing into a gas so fast. You can't, like, I can't store dry ice here. We have to get it from a special place that has special cooling technology, because it's not even like I could just put it in a normal freezer and make dry ice, whereas with water, it will stay ice, right? It wants to be a solid. So, and whereas this wants to change into, it doesn't want to be a solid. It wants to change back, okay? So, hydrogen bonds are strong. And then we called dipole-dipole middle strong yesterday. I know that's weird. Or middle strength, I think. So this one is dispersion. So weakest. I probably should have put these in order, but that's okay. This is dipole. And then hydrogen bonding is the strongest. So basically, we already did this. We're just saying, okay, so yes, these forces have a variety of strengths, and that correlates into, if you make them a solid, they'll have the same sort of properties. Yes. Hydrogen and NOF, right? Nitrogen, oxygen, and fluorine. Yep. HNHOHF. Yes. Okay, so in grade 11, we just keep it simple. You just pick one of the three. Technically, everything has dispersion, but nonpolar, it's only dispersion. So then dipole would be, or polar could be dipole, and dispersion, but we just kind of focus on the unique ones. That's why. So okay, so you're going to talk about what kind of particles make these up, molecules, what kind of forces, depends on what kind of molecule it is. And then the other thing that we're going to talk about is whether it conducts electricity and maybe heat. So you wouldn't really consider natural gas or carbon dioxide or water conducting electricity because they don't, right? It's not an important property. But this is a difference between these solids and ionic and metallic, okay? So that's why this is in here, to say it's not expected to conduct electricity. Actually, we did a lab last year, right, where you tested the properties, and the covalent molecules did not conduct electricity. Okay, so then this is one that you probably have not considered before. But network solids, they are important to us humans. And here it says atoms. When some of the textbook questions ask you, they give you the atom, or the formula like CO2 or NaCl, and it wants you to pick what kind of solid it would be. So when it says atoms for a network solid, they don't just mean any atom. So it's really specifically carbon or silicon. So they're in that column together where there's 4 valence electrons. And up until now, we sort of said, oh yeah, skip that column. Remember, we're not going to skip it anymore. And the first thing we're going to talk about is what happens when you have carbon, or silicon. So because they have 4 valence electrons, then plenty of weird things can happen. They can bond to each other. They can double, single, triple bond to each other. They can double, or you guys did CO2 yesterday, double bond. The CN one, which is weird, was a triple bond. So lots of weird things can happen when you have carbon. So actually, I think this diagram is in your note. And so you have covalent bonds, which are very strong. So let's highlight that. And the very strong, oh, it says it again. Covalent bonds 2 times, okay? So covalent bonds, those are actually intramolecular forces. They are very strong, okay? So you can have lots of bonds or only a few bonds. And that's why you get a wide variety. So it depends on how many bonds basically you have. So we're going to talk about the difference between graphite and diamond. Silicon or silica is also important. Sand, quartz, those are silicates. But since we are carbon-based organisms, then you're just more used to carbon. But definitely silica will do the same, or silicon will do the same thing because it has 4 valence electrons. You guys have this, right? So these 2 are representations of this. So it's not that I'm going to ask you to reproduce these, but I just want to show you the importance of, when you make a solid, the importance of the kind of bond and how many there are sometimes. So these are both carbon-based. Which makes them allotropes, if you've ever heard that word before. And really, it's the nature of how they're arranged in relation to each other. So this is a representation of graphite, so similar to this. So what it's trying to show, like this is a sheet of graphite, we call it. then there's space in between, and then there's another sheet of graphite, and then a space in between, and another sheet of graphite. So all the black means carbon. If you burn something that's carbon-based, it's going to turn black. Like if you have a campfire, what's left over? Soot, right? Black, that's carbon. So you can see that it's still pretty ordered, right? The structure has pattern to it. Yeah? Okay? And this is sheets. So if you think about the sheets on your bed, you can pull them, right? Sheets move. So in your pencil, we call it pencil lead, but it's really not lead. Lead is toxic. That would not be good. It is graphite. So you can sharpen the graphite. You could shave it off with a knife. Like you can manipulate the graphite. This is also carbon, but this is representative of diamond. So again, you can see that there is pattern to it, but you can see when you look at it like this, the layers are connected to each other. So these extra connections, and they've chosen here angry red, right, to emphasize the strength of these connections. That makes this molecule, this solid, so much stronger. So these extra covalent connections that don't exist in the sheets of graphite make diamond the hardest substance on Earth. You're not going to put diamond, real diamond, in a pencil sharpener and sharpen it, right? That's not going to happen. So, the thousands of years of the pressure in the Earth and crushing carbon atoms, making diamond, has made the solid so much tighter because of these extra crosslinks, okay? So that's what this picture is trying to show. And it even, like these are way thicker, it's even trying to show that, yeah, these are connected to each other, but it's not as strong. They've used a dashed line, okay? And then the newest kind, is buckyballs, okay? So these are also carbon, named after Buckminster Fuller. Yeah, so poor guy, okay? And this is revolutionary. And again, those of you that are interested in science, you may choose to study this. So they want to use these carbon arrangements to make nanotubes and nanotechnology, and to try to do things with medicine that we can't do right now because our cells reject foreign material. They want to try to make a carbon nanotube ladder up to space, okay? So actually I love this video, one of these that we can watch. This, didn't I? So when you have a network solid, they are definitely very strong, which means that they are hard. They have very high melting points because covalent bonds are strong. And if you want, you can even add to this just to remind yourself that, in fact, a covalent bond is intramolecular, which it does say earlier in your note, but if you want to put it there as well. And then one of the not good things about graphite and diamond, well, it's good and bad, I guess. The electrons are not free to move, so they don't conduct. Which is good for insulation, but not good if you want a conductor. And then these pictures here, so this is different kinds of silicates. So this could be like the silicate found in sand or something like that. So again, you don't have to reproduce these, but you can see that it's sort of forming similar kinds of shapes to carbon because they have 4 valence electrons. This is also trying to show you what we're going to do tomorrow, which is a 3D shape. So because it has 4 valence electrons in a 3D way, it creates what we call a tetrahedron, tetra for 4, okay? So you don't have to draw these. Or like label or recognize, you know, it's just cool. So like the guy said in the video, nanotechnology is sort of a new frontier, not just in chemistry, engineering. You can do nanotechnology with other materials. You don't have to just use carbon. So maybe that'll be your thing. Okay, so ionic solids or crystals, easy peasy. Ionic crystals have ions, and they're formed by ionic bonds. Wonderful, okay? And it's a very regular pattern. We talked about how boring ionic bonds are before. You get plus, minus, plus, minus, plus, minus, plus, minus. Some of the ions are very tiny. So last year we did whether something was soluble or insoluble. Usually that's based on the size of the ion. And again, should you continue in chemistry, then perhaps you will actually calculate that space between the ions. So it's sometimes called packing, the packing structure. You can definitely calculate the distance. We are not going to do that, okay? They have high melting points. And then again, if you've got stronger forces, if you have small ions, then it's going to take more energy to get them apart. In the tune of like 680 degrees Celsius, you know? So you don't really think of, for example, sodium chloride, like table salt, you wouldn't even think of that melting that, right? That doesn't make sense. You think of it as a solid. Because the forces are so strong, then the energy required is it's not really reasonable. We don't have equipment in here to do 618 degrees Celsius. For good reason, really. So this is just an example of the crystal lattice, like the repeating pattern. Again, it's trying to show that the anions are bigger. Actually, I just did that in my grade 11 class today when we did trends. Because anions gain electrons, they get bigger. And because cations lose electrons, they get smaller. So this picture is trying to show that. Again, you can see here that it looks like a cube, right? So that's really when you make a solid, that's the structure that's sort of prevalent when you have a repeating pattern. And I wouldn't make you reproduce this picture either, okay? Just for your information. Okay, so they are very hard, very high melting point because ionic bonds are so strong. They are very brittle. So this word here, that they're directional, this is definitely a word your textbook uses. So if something is brittle, it means that it doesn't bend, it's not really flexible. So again, if you think about table salt, that it forms a crystal, it's sort of obvious, but your textbook talks about the idea that if there's a plus and a minus, then we call that bond directional. basically what it means is if you have like a strong pattern, then when you break the bond, it's gonna shatter instead of bend. Okay? And then we did this last year as well. It is going to be conductive only when you dissolve it in water. We called that electrolyte, an electrolyte solution. You need, so the bonds are so strong, when they're stuck together, there's no plus minus. You need the ions, we called it mobilized or free. So the ions need to be mobilized, free to move, so you can provide a path for the electricity. Okay, and then last but not least, metallic bonds or solids. Oh, so how wonderful they have metallic bonds. And again, this is in the note earlier, but if you want to rewrite it here, metallic bonds are transition metals. They can conduct electricity. I don't know why I didn't spell the full word, but that's okay. So the reason that they can conduct electricity when they're a solid is because the electrons are already free. So delocalized means free, basically. It has no particular spot. So then again, there's that word non-directional. That's definitely something specific to your textbook. That means that there is no plus minus repeating rigid pattern, okay? The electrons are free to move around, which means that it can conduct heat and electricity. So we have copper wiring in our homes. You might have copper pots in your house, for example. And then the next page, again, is just a diagram trying to show what this means. So the electrons are kind of all over the place. They are not in a particular orbit or anything. So they're just kind of randomly moving, okay? So these solids, so the freely moving valence electrons mean that they are flexible, so can be drawn into wires or hammered into sheets. You can do that instead of brittle where they're just going to shatter. And conduct electricity in the solid form. There is still attraction with charge because it's still a little bit plus and minus. So they are hard and have a crystalline shape. Okay, so if you just look at this worksheet for a second, because it's kind of weird. It's just a different way of doing the questions. And if you didn't get one, I have one here. So it's at the back. So what this sheet wants you to do, so it's got headings, particles and crystal, which match up here. Attraction between particles, melting and boiling point. You need all three. Okay, so you can see the headings match up here, okay? So then these phrases go in this column. These phrases go in this column, okay? So they match. And what you're trying to do is say, okay, what kind of particles are in metallic crystals? Positive nuclei surrounded by a sea of electrons. That was just in the note. So I'm going to write number 2, okay? And then you go through them. So it's really just general. See what you can do. The row should add up to 126. Okay, so it's just a different way of trying to do the worksheet. The solution for this is on the back and on D2L. Okay, the textbook questions, they get you to look more specific. Like if you have H2O, for example, what kind of solid would it be? So you can give those a try. You can work on your assignment, work on the gizmo. You can use a computer or your phone if you can get on the Wi-Fi. And I will give out the test review. You could do that as well, okay? After lunch, I will set up the gas discharge tube.